Hello students, today we will be discussing the risk and BGI potential assessment tool. This is continuation of this particular module, that is the future urban ecosystem. In this first I will bring the summary of the module 2 before we come to the discussion of the BGI. So in the module 2 we had the major discussion on the ecosystem types, concepts and theories. The sixth lecture, it was on ecosystem types. Ecosystems are classified by physical environment, terrestrial, aquatic, and human influence, artificial. That is also the urban ecosystem as well. Terrestrial ecosystems, forests, grasslands, deserts are defined by climate, soil, and vegetation patterns. We discussed aquatic ecosystems, which distinguish between freshwater, lentic, lotic, and marine systems based on salinity and flow. Interconnectivity between these ecosystem types that ensures that all living and non-living components influence one another across ecosystem boundaries. So the keywords for this lecture 6 was terrestrial, aquatic, transitional, artificial ecosystems and interconnectivity. It's really good to remember all lectures as well. Lecture 7 was on ecosystem types, case examples like specific concept we discussed, ecosystem performance, unique global functions such as carbon sequestration in boreal forest. Transitional ecosystems like mangroves, Sundarbans act as critical buffers against storms and coastal erosion. Wetlands function as the kidneys of the landscape, purifying water and recharging groundwater aquifers. And we also know wetlands can take care of the sewage water as well. Microbial ecosystems, soil and gut microbiomes, they are almost invisible but one of the most important partners for these ecosystems to function properly. They drive essential decomposition and nutrient cycling processes. The keywords for this lecture was carbon sequestration, Sundarbans, wetlands, microbiome, transitional ecosystems. Lecture 8 was on ecosystem concepts, where we discussed that ecosystems are understood through structural units, functional processes, and dynamic system states. The ecological niche describes a species, profession, what role it plays, and address its habitat within the system. Keystone species like sea otters, who play a disproportionately large role in maintaining ecosystem structure relative to their abundance. They may be small in numbers, but they are actually exerting immense influence into the balance of this ecosystem. Population oscillation, which refers to the cyclical fluctuation of predator and prey population, links and here example we had actually discussed there in details. The keywords are ecological niche, keystone species, population oscillation, Lotka-Volterra model for prey and predator. In the next lecture, under the ecosystem theories, we discuss the key concept of theory which evolved from foundational energy flow models to complex social ecological systems, SES. Later on, we also discuss ACTS. Linman's trophic concept highlights the inefficiency of energy transfer. Only around 10% moves up in each and every trophic level. Resilience theory, which explains how systems absorb disturbance and reorganize without collapsing into a different state. The intermediate disturbance hypothesis, which suggests moderate disturbance maximizes biodiversity by balancing the computation. So, a little bit of competition is always good. So, the keywords are SES, resilience theory, panarchy, intermediate disturbance hypothesis, etc. In the last lecture of that module was on demonstration of ecosystem theory and concept. Key concept was ecosystem interactions lead to synergies, mutual benefits or trade-offs, compromising one outcome for another. The oak pine shift in the Himalayas, we discuss this as a good case which illustrate retrogression, where stable oak forests are replaced by fire prone pine, is also having the governance side. Oak acts as a keystone species whose removal triggers top down cascades, loss of biodiversity, and soil degradation. This shift represents a transition to an alternative stable state driven by chronic anthropogenic disturbance. Keywords are oak pine shift, synergy, trade offs, retrogression, alternative stable states. So, I believe you will go back and you will look at these 5 lectures once. Now, for today, we will be discussing risk and BGI potential assessment tool. We will be referring to more than one tool and we will be discussing one particular tool in detail. BGI and its context, we will start with risk assessment, BGI potential assessment, synthesis and prioritization, case studies applying the tool in the Indian context, implementation and governance. The context, blue-green infrastructure as critical infrastructure. By definition, this is an interconnected network of natural and semi-natural components, green spaces, water bodies, which are designed to deliver ecosystem services. We have discussed it in detail in Module 9, lecture number 41. The shift is moving from grey, which is single purpose fail safe, to blue green, multifunctional, safe to fail. Indian context in cities like Bangalore, Chennai, and actually almost all the cities now are really having the right case to go for BGI because for them BGI is not just an aesthetic requirements anymore, it is a flood mitigation and heat reduction necessity. Also, it is going to help them in air pollution managing and as well as the groundwater depletion control. The planning gap, planners often know what to build like a biosoil but struggle with where to place it for maximum impact. So, our discussion will try to go towards that. The planning under uncertainty. That is very, very important to take note on that this is the particular era when nothing is certain. Stationarity is dead. Past rainfall records are no longer reliable predictors for the future storms due to climate change. We face deep uncertainty regarding the frequency, intensity, and duration of extreme events. We can see how the snowfall patterns are also changing. So, precipitation pattern globally has really becoming a very uncertain phenomenon. This uncertainty demands a shift from predict and prevent, which is always necessary because in the engineering we always go for the certainty. And now we are shifting towards assess and adapt, which is risk based prioritization. Engineering certainty is not working anymore. Urban planners must manage uncertain future climates, and we need a decision support system to identify no regret interventions, projects that yield benefits regardless of how the climate shifts. So, now we will be discussing the risk assessment where we will be discussing not only the risk is changing, but also how we assess that is also improving because we are having now access to many advanced tools and techniques. Deconstructing risk, we discussed risk previously also. The risk equation, I think all of us will remember that risk is a function of hazard, exposure, and vulnerability. And in many cases, we also talked about the coping capacity. The hazard, the physical events like rainfall intensity, heat waves. I have given a number here, but it again depends on the context. We cannot eliminate this, but we can map it. Exposure, who and what is in threat. Population density, critical infrastructure in floodplains, they are good indicator towards the exposure. Vulnerability, the predisposition to be adversely affected. Poverty, kacha housing, lack of insurance, age, these are some of the vulnerability indicators. resilience, ability of communities or infrastructure to absorb or recover from shocks. So, this is just we can say inverse to the concept of risk. So, to plan effectively, we need maps of where risks and opportunities overlap. In our module 8, lecture 36 covers risk in depth. Now, the risk assessment, the demand side. The objective is where does the city need help? Where is the ecosystem stressed? Where are human populations most threatened? So, to answer these questions, we can actually map the demand for ecosystem services. Understanding these questions will be very helpful. Primary hazards in Indian cities: urban flooding, waterlogging due to drainage failure, heat stress, UHI effect, pollution, anthropogenic activities. And in today's time, whenever we are discussing flooding, we are also discussing drought. So, the methodology, it can be geosemantic framework which helps in identification of risk hotspot and potential implementation zones. And this we will be discussing later. But today we will be discussing some other tool. Spatial superposition of hazard, exposure and vulnerability layers using GIS is actually common in both the tools. Mapping hazard, urban flood risk, input data, high resolution digital elevation model for slope and flow accumulation is used. Rainfall data, IMD graded data, 12 kilometer resolution. Modeling approach, you need to really go for this basics of hydrology, soil conservation service curve numbers, we call it CN number, SCSCN number. Calculate the surface runoff based on land use and soil type. And the equation of runoff is very easy to understand. It talks about the rainfall, initial abstraction, and the potential maximum retention. And the correlation between these three parameters are actually going to be the runoff. So, the rainfall is the trigger, initial abstraction as well as retention will keep it hold, and then the runoff will happen. Output, a map showing potential waterlogging depth and velocity. Mapping hazard, the heat stress. It is often termed as invisible disaster because it lacks the visual destruction of a flood but more lethal. What are the input data here? LST, which is derived from Landsat 8 or 9 or Moody's thermal bands. Air temperature, local weather stations for calibration. We discussed it, how to really take care of it and how IMD guides us. Advanced indicators like heat index. Now we are not talking about temperature alone, combining temperature and RH. High humidity in coastal cities like Mumbai, Chennai, even 35 degrees Celsius will be like feeling like 45 degrees Celsius. So that's very lethal. The warm night phenomena, assessing not just daytime peaks but also the failure of cities to cool down at night, so that UHI impact can be captured through this warm night phenomena. Mapping vulnerability, the ACTS framework, socio-ecological technological systems approach to vulnerability, social vulnerability, census data. Density, caste, tribe, marginalization, literacy, age, ecological vulnerability, lack of green cover, distance to water bodies, etc. Technological vulnerability, distance from hospitals, lack of storm drains, poor road access. So, we can synthesize that vulnerability can be represented by a composite vulnerability index. These factors, often using AHP analytical hierarchy process, we can create that composite vulnerability index. BGI potential assessment, the potential assessment, the supply side. So, we have seen the demand side, now we would like to see that what BGI can offer. To map the supply capacity, where can we intervene? That's a very, very important question. Constraint check, not every high risk area is suitable for every BGI. Not every high risk area can support a wetland. Steep slopes may prohibit the construction of retention ponds, and dense concrete courts may lack the space for large parks. So, these are the very typical type of constraints. The supply assessment relies on physical geography and urban morphology. The literature identifies several non negotiable criteria for BGI suitability. So, suitability analysis, a GIS MCDA, multi criteria decision analysis approach to finding feasible sites, and geosynthetic framework actually takes care of this particular multi criteria decision analysis as well, but it also talks about the solution. And geosynthetic helps in identification of risk hotspot and potential implementation zones. Biophysical criteria, topography. Slope is the critical determinant for water retention. Flat areas, which are ideal for infiltration basins, wetlands, and large retention ponds. Moderate slopes, suitable for swells because you are getting a natural slope there, and conveyance structures. Steep slopes, unsuitable for retention due to flow velocity but critical for stabilization and afforestation to prevent landslides. The direction a slope faces that determines solar radiation receipt. This influences evapotranspiration rates and the viability of specific plant species for green roofs or walls. In the northern hemisphere, south facing slopes are hotter and drier, requiring drought tolerant species. So, that's the way topography helps you in taking the right decision in the BGI. Next criteria, biophysical, is the soil and hydrology. Infiltration capacity. The USDA hydrologic soil groups A, B, C, D are the gold standard for assessment. Group A, sandy, high infiltration, ideal for rain gardens and permeable pavements. Group D is clay, low infiltration, and the rest are within. Low infiltration, common in many Indian river deltas like Kolkata, parts of Chennai. These soils require storage or detention based BGI like ponds rather than infiltration based solutions or significant soil. Groundwater level, a shallow groundwater table common in coastal cities that limits the depth of infiltration trenches. If water table is at 1 meter, a 2-meter deep soak pit is useless. So that's the way we take advantage of our knowledge on the soil and hydrology. The third biophysical criteria is land use and availability. Land use, land cover classification. Satellite imagery allows us to classify land into built up vegetation, water, and open or barren lands. Space syntax and opportunity mapping. The assessment must identify opportunity spaces. In dense Indian cities where open land is scarce, the concept of retrofit potential becomes a key metric. This involves calculating the available roof area for green roofs or the length of the road network suitable for bioswales. So, we look for grey to green parking lots, wide road medians, concrete nalas, roof area potential for green roofs in commercial districts, brownfields, post industrial sites. So, the GIS multi-criteria decision analysis workflow for potential mapping has a process which integrates the disparate physical variables into a single suitability index. This is a rigorous mathematical process. First, it defines the criteria: slope, soil, LULC, distance to stream. Second step is standardization. Convert all values to 0 to 1 so that you can create. This normalization will help you in compatibility. The third stage is weighting. AHP, analytical hierarchy process, is the most oftenly used tool. Expert judgment determines importance. Entropy method, data driven objective weighting is also can be opted. Overlay or aggregation, then you go for suitability. For each matrix, the score is weighted and then you go for a summation. The GIS MCDA workflow for potential mapping, problem definition, constraint mapping, factor standardization, weighting and aggregation, and key tools as I discussed, and you can read this description of your own. Scoring suitability in the slope, low and high suitability that has been mapped in this table for slope, soil, land cover, proximity to drain. A pixel based map is the result, where red is impossible to build and green is ideal for BGI. So, the suitability map, the final output is a BGI potential map categorizing the city into high potential areas with flat slopes, permeable soils, and available space. Moderate potential areas requiring engineering interventions like soil replacement under drains to function. Low potential areas physically unsuited for standard BGI. Steep rock faces, dense industrial seal, like that. The supply demand mismatch common findings are that areas with the highest potential, peri-urban, open land, often have the lowest risk, low population. The trap is that planners often pick the easy sites, high potential, rather than the necessary sites which is having high risk. So it has to be balanced. So the goal shall be to find an overlap. Synthesis and the prioritization for this multi-criteria decision analysis, we can look at the core decision tools like high risk, high potential, the sweet spots, and the priority can be in immediate implementation. You can go for rain gardens, bioswale, constructed wetlands, urban forest. Whereas the high risk but low potential engineering challenge, priority shall be hybrid grey green solutions, and you have a number of options for that. Low risk, high potential, the conservation zone, priority 3, that is the protection and future proofing is best for these type of areas. So preservation of existing wetlands, riparian buffers, agroforestry, spawn zones, creation, these are the recommended BGI. And where it is low risk, low potential, it's a monitoring zone and you can go for the fourth priority, that's the observation. Street trees, spotted greenery, awareness campaigns, they are very helpful. Prioritization logic, urgency versus feasibility. When the quadrant 1 is the obvious starting point, the prioritization logic can be further refined using a tripartite framework of urgency, feasibility, and synergy. What is the urgency? Derived from the risk layer. How many people are affected? Is it life threatening? Feasibility derived from the potential layer and land ownership data. Is the land public or private? Is it legally encumbered? The synergy is where we have to come at the end, that is, does a project here connect two existing green patches? Landscape connectivity matrix, a project that links two habitat offers a synergy bonus that might bump it up the priority list even if the risk is slightly lower because you are getting some additional benefit here. Case studies applying the tool in the Indian context. Jaipur, planning for heat and water scarcity. Jaipur faces a dual crisis, a semi arid climate with rapid loss of green cover and severe groundwater depletion. A study utilizing GIS MCDA integrated LST, NDVI, and precipitation data. The use of entropy based weighting was crucial here to remove subjective bias. The model identified that 35% of the city, particularly peri-urban regions and river corridors, fell into the high potential category. In arid zones, BGI potential is dictated by water availability to sustain the green. So, prioritizing drought tolerant species will be probably a good option. Chennai and Tirunelveli, managing the flood drought cycle, coastal typology, flat terrain, and the loss of critical marshlands. The challenge is managing the massive monsoon pulse. So the assessment was done and LULC analysis with SCSC and runoff modeling, and in Tirunelveli The analysis mapped 13 interconnected water tanks. High water table restricts infiltration. Focus on blue over green, restoring the connectivity between temple tanks, the areas, and macro drains. That was the intervention suggested. Connectivity is the critical potential factor in coastal flood management, and that's the great lesson out of this initiative. In the Himalayan cities, the slope constraint is there, fragile ecosystem, high slope instability, and rapid urbanization on gradients. The flat land is built up. New development is pushing onto dangerous slopes. The assessment was done using the landscape matrix, patch size, edge density, and morphological spatial pattern analysis. And the methodology highlights slope acts as a double-edged sword in the MCDA. It is a constraint for water retention, water moves too fast, but a high risk factor for landslides. So the intervention suggested was core and edge preservation, BGI used for soil stabilization rather than just water retention. So the lesson learned is in hill cities, BGI must respect the angle of repose. Vegetation helps anchoring the soil. Implementation and governance of this BGI, from maps to action, breaking the silos, the barrier, we have discussed them. Road department builds the drains, parks department plants the trees, and nobody takes care of the biosoils which has been created. So drains and trees together, the biosoil, nobody is taking care. The solution is the risk potential map as a boundary objective. It forces departments to collaborate because the map shows the shared risks and shared opportunities. Institutional shift, BGI requires a socio-technical transition, not just new technology. The map is not the territory and the tool is not the solution. Operationalizing the future requires embedding these technical assessments into governance structures. Participatory planning, democratizing the data, top down GIS assessment often miss local realities, like a vacant lot in GIS might be a community cricket ground or a sacred grove. The future of urban ecosystems that requires participatory GIS. Participation must go beyond consultation. It requires co-design where citizens validate the risk layer. Does this street actually flood? The census say no, but the people say yes. And the potential layer, will the community maintain this bioswale? That is the question then can be brought in front of the people. So though we have discussed it previously also, but you can see how important it is for the future as well. The blue-green city coaching model, this approach involves coaching municipal officials and the stakeholders to use the tools and ensuring that the technical outputs like scenarios, cost benefit analysis are understood appropriately and owned by the decision makers. Economic valuation and trade-offs, cost benefit analysis, we must move beyond construction cost to life cycle cost. Grey infrastructures depreciates, green infrastructure appreciates. A BGI project costing 1 crore is viable if it is preventing 5 crores of flood damage. That's the way the valuation shall be done, avoided risk. The risk map allows us to quantify this avoided damage. The co-benefits in Jaipur, BGI was valued for energy savings, reduced AC loads. In Kolkata, the East Kolkata wetland provide livelihood, fisheries, agriculture for thousands. The tool must capture these livelihood services. Trade-offs. The tool must transparently show trade-offs as well. The risk versus potential matrix helps visualize the cost of inaction, high risk, to justify the investment as well. We can see there is a good potential to be that BGI can be integrated with the national framework. Already the climate smart cities assessment framework is integrating it and identified indicators like urban planning, green cover, biodiversity. URD PFI guidelines talks about 330-300 rule that has been adopted. 3 trees visible from my window, 30% canopy area in and around my plot, and 300 meter to park. So that's the concept of 330-300. Roll up the tool. These tools provide the evidence base which are required to improve the city's climate smart ranking and access funding. So today's summary, we talked about risk, we talked about BGI potential, we talked about risk potential matrix and prioritization strategies. And we have also discussed the relevant methodological tools. And we should not forget the initial summary part of the module 2 as well. These are the references for you. Thank you.